All right, today we're going to look at some probability trees. And we're going to look at it for two different types. So we're going to jump straight in, essentially at the deep end here. Really do, it's kind of both types of probability really that this covers. And broadly, these come under independent events or dependent events. Independent events are events that, one is independent of the other. The probability of something happening is not related to the probability of something else. That doesn't say that we can't work out the probability of both events happening. It's just that whether one happens or not doesn't affect the other. But with dependent, it does affect it. So the outcome of one effect will affect the probability of the next one happening. So one event changes the probability for the other event. Independent doesn't change it at all, completely independent of each other. The other one is dependent. Okay, so I've got 1, 2, 3, 4, 5, 6, 7 different kind of sets of events here, both of which have two things in it, two events we'd call it, and I want you to decide whether each one is independent or dependent. So maybe pause the video here now. I haven't got a pause button coming up on screen, but you can pause, have a little think, maybe write them down in two lists, but definitely have a little think about which one is which, and then unpause when you're done. Okay, so presumably you've unpaused or just let it run through because you didn't listen to what I said, but that's fine. No one listens. Okay, so a ball is selected at random from a bag, replaced, and another taken. Right, this is definitely independent. Classic independent event. We've got a ball full of counters or balls, or what, a bag full of balls, you know what I mean. Right, and so we take one out, we record the colour, put it back in. Because we put it back in, there's the same amount the next time we take a ball out. So the probabilities haven't changed, and we put it back, take another one out. Every time you've got the same probability of getting either a different colour or number, whatever's on those balls. Okay, a coin is flipped and a dice is rolled. Two things. Well, obviously it doesn't matter what you get when you flip the coin. The probability of each number on the dice is exactly the same. Again, it's an independent event. One event doesn't affect the other. Right, a train is late leaving one station, and whether it's late to the next one. Well, I think if it's late out of one station, I think it's pretty likely. That's definitely going to affect whether it's more likely to be late to the next station. Because if you've already started off late, you're more likely to end up late. I'd say it's a dependent event. Someone's gender and which sandwich they choose for lunch. Now, I'm sure someone could probably do some study to say that women are more likely to choose one particular flavour and men are more likely to choose another. But actually, it doesn't have an effect. I think we could safely say that's probably completely independent what someone's gender is and what they're for lunch. Maybe slightly controversial, but there's no particular study that I know of that means that it changes the gender, affects what flavour you might have for lunch. A ball is selected at random from a bag, not replaced, and another taken. Now, the not replaced is the important bit, because this means it's dependent. So you've taken one ball out of the bag. There's now one less ball in the bag. There's, one fewer, I should say, ball in the bag. And so the number of balls has changed, and depending which colour you've selected out of the bag, obviously is going to change that. If you selected the blue, there's one less blue, but if you selected a red, there's one less red. So that does affect it. The first outcome affects the probabilities for the next outcome. Dependence. The score on you, I was thinking that's supposed to say your, the score on your science test and the colour of your shoe as well. Again, I'm sure someone could do some ridiculous study into that, but I think it's safe to say that's going to be independent usually. The score in your science test has nothing to do with the colour of your shoes. Last one, let's put a little R in there just so it's your. Someone's gender and whether they are left-handed. Oh, now this one's definitely a little bit controversial. I looked this up. I thought this would be completely independent, but it turns out it's dependent, actually. You have a slightly higher chance of being left-handed if you are, well, I can't remember if it's male or female, but definitely one of them, you have a higher chance of being left-handed if you're one particular gender. Okay, and I can't remember what the study said, but trust me, it was dependent. Now, if you put independent, that wouldn't, I'm not surprised, and a lot of people probably think it is independent, but apparently there is just a slightly different probability for whether you're left-handed depending on gender. Okay, though. Right, so, but first of all, we're going to look at independent events. So these are probability trees for independent events. I'm sure you've seen these before. If you haven't, you might want to just go over this again, because I might go a little bit swift. But I am basically going to start from the start here with the basic form of a probability tree. Now, a probability tree for one event would be a bit rubbish. Let's say we've got two outcomes. We've got outcome A and outcome B. Well, that would be my probability tree. You see, you effectively imagine that you start at the start here where I've put a little star, and then you've got two choices. Either you get outcome A or outcome B. Or I say choices, two eventualities, two outcomes. So one event on a probability tree is a bit of a waste of time. Generally, we'd use it for two or more outcomes. Or events, sorry, not outcomes, events. Now, PA, this is the probability of A. We put that along the branch. So at the end of the branch, we have the outcome. So in this case, I go along this branch. I've had outcome A. I've selected the blue ball from the bag or whatever outcome A is. The probability of getting that goes along the branch, and the same with probability of B. That goes along the branch towards outcome B. Okay, as I say, now we'd usually use this for at least two or more events, so we need another set of branches. So we need a set of branches for every outcome that we got before. Let's say we got outcome A. Well, next time we've got the same possible outcomes, outcome A and outcome B. So I need a set of branches from outcome A, so I could then get A or B again. And again, probabilities go along the branches. But of course, I might have got outcome B. I might be coming down this bottom path. I might have picked that ball out of the bag and it's red, outcome B. In which case, I need a set of branches down here to again cover my two outcomes and the probabilities along the branches. So what have we got here? What this actually shows us are the four different possible outcomes that I could have had. All four of them at the end. When you get to the end of the tree, you've already got all the different outcomes you might get. Now this first one would be A and then A. This one here would be A and then B. And this bottom one here would be I get B first, and then A. See that? I get B and then A. And this bottom branch all the way across here would be outcome B, and then outcome B again. Okay? And at the end here, we'd usually put then probabilities. Let's just add this in just for completeness. So at the end here, I could work out, if I had the probabilities on here, the probability of getting A and then A, the probability of getting A and then B, the probability of getting B and then A. It's all just down to what path you got to get there, and then the probability of B and B. All right, so main things to take away from this. Each set of probabilities on each set of branches must add to 1. Right, because at each stage, you're either going to go, say, along this branch or this branch, or if I had 3, I'd be getting one of the 3. So it's certain I'm getting one of them. Remember, certain in maths in probability is 1. And so the sets of probabilities must add to 1. So these ones would add to 1. But also, these pair here will add to 1, and so will that pair down there. So basic things to take away from this. Label the outcome at the end of each branch. Label the probability along the branch. The probability goes somewhere along the branch. And the probabilities on each set of branches must add to 1. Yep. Okay, let's do that then. So let's do it for flipping a coin twice. So if I flip a coin once, I've got 2 outcomes, heads or tails. Now the probability of getting a heads, I think we should be pretty comfortable with this, is 1 out of 2. There are 2 options, and heads is one of them, and tails is also a half. Okay, now if I flip the coin a second time, I need another set of branches. So if let's say I went up this way, I got a heads. Well, I've got 2 options for my second coin, heads again, or tails. And of course, the probability of heads is still a half because it's independent. It doesn't matter what I got on the first coin flip, I've still got the same probability on the second. And half again for tails. But of course, I might not have got a heads the first time. I might have got a tails. And so I've got 2 options again, either heads or tails. Again, probabilities along the branches. And notice that this set of probabilities adds to 1. A half plus a half makes a whole. So that is your basic probability tree. Again, each set of branches adds up to 1. So there's my tree for it. How about we think about our rules for probability? Remember we said if I want and, I've got to multiply. So let's say I want a probability of a heads and another heads. Well, this means I multiply. As you go along the branches, you times. So you take the probability of your first outcome and the probability of your second outcome, and I'm saying a heads and a heads, so you times. Well, a half times a half is a quarter. And I could do this one here. Let's say I want the probability of getting a heads and then a tails. Well, that would be a half for the heads and a half again for the tails. The coin is a bit boring, it's got to be said, because all the probabilities look pretty similar. And then I could also do the probability of tails and then heads. And it is important that we notice the order of these. Again, probability of tails is the half, heads is the half. I want tails and heads, so I multiply. As you go along these branches, when you go along your path, you multiply those probabilities together. As I say, the coin is a bit rubbish because it's just so obvious. Oh, that shouldn't be times, that should be equals. Yeah, what about if I want or? Let's say I want or. I want to get, say, the probability of heads and heads, or the probability of tails and tails. Well, that's going to be or. That's going to be add. So I'd have to do a quarter plus a quarter, which equals 2 quarters, or a half. So as you go down this end, that would be putting more than one of these together. I might want heads and heads, or tails and tails. You add. So we're going along the branches, we multiply, going down the branches or down the outcomes at the end, and you want more than one, you add because you want that one or that one, for example. Okay, right, let's do a proper one then. So Rebecca has 9 coloured beads in a bag. Good for Rebecca. 4 of the beads are black and the rest are green. She removes a bead at random from the bag and notes the colour before replacing it. Now, because it's replaced, this means we have an independent event. The outcome of the first one doesn't affect the outcome of the second because she then chooses a second bead. Calculate the probability that Rebecca chooses 2 green beads, or 1 black and 1 green. Okay, let's do our probability tree then. So let's get 2 sets of branches for bead 1. Let's put a little title up there. Bead 1 and bead 2. We might get, let's do a little bit of colour flipping here as well. She could get black or green, black or green, and black or green. Green. So black or green, black or green, black or green. Let's do the probability of black first. There are 4 of the beads are black, so that's 4 out of 9, because there are 9 in total, so it's 4 out of 9. And let's do the green. Now the green, if there are 4 black, 9 take away 4 equals 5. There must be 5 green, so that's 5 out of 9. Notice 4 ninths plus 5 ninths make 9 ninths, that's 1. So that is a complete set of probabilities. Now on my second set of branches, the probabilities will be the same because it's been replaced. So she takes a bead out, she puts it back in, we've got the same amount of beads. So we've got 4 ninths for that one and 4 ninths for that one. Okay, then let's go for the green. We have 5 ninths and we have 5 ninths, because the probabilities on the second set of branches are the same. Right, now let's just go to a blue pen, I think. So calculate the probability that Rebecca chooses 2 green beads. Now there's only one path to get 2 greens. That would be down here. We get 1 green, we get another green. So that's green and green. We're doing and, we're going along the branches, and means multiply. So I need 5/9 times by 5/9. Multiply the tops, multiply the bottoms. 5 5s are 25, 9 9s are 81. Okay, so the probability of 2 green beads is just that. There's only one option for 2 green beads, and that's it. Let's just change colour and let's go to red. Okay, next one. 1 black and 1 green. Now there are 2 ways that I could get 1 black and 1 green. There is indeed the way where I get a black first and then a green. But also, I could do it the other way round. I could get green and then black, because it doesn't state the order in the question. It just says 1 black and 1 green. So I could get green and then black. So there are 2 options for this one. Now the first one, I do black first, so that's 4/9, and then green, which is 5/9, and I'm going to multiply them together because it's and black and then green, which is 4 5s are 20, 9 9s are 81. This is why we don't generally simplify, because it's now going to make it easy to add some together if I need to. Now green and then black, well, that green is 5/9 going along this path, and then black is 4/9 going along that path. 4 5s 20 over 81. Now I have got 2 outcomes here. I could get this outcome, and then I could get this outcome. So this one or this one. Remember, or is add. So you take those 2 probabilities. Oh, I think I might sneeze. Yeah. I'll turn the mic off in time. Whew. Okay, so 20/81. 20 over 81 plus 20 over 81, because I want this outcome or this outcome. They both satisfy the question. So that's 40/81. 40 over 81. Okay? So along the branches you multiply. If you have more than one outcome, you add, because they're that one or that one. I think it's your turn to properly do one now. So Simon has a biased coin of which the probability of 0.68 of landing on heads, which has a probability of 0.68. Okay, so we're working in a decimal here. That's fine, because we can work with decimals. It works just the same. You can use your calculator for multiplying the decimals when you need to. And he's going to flip the coin twice. So there's our 2 events: flipping it once, flipping it twice. And of course these are independent, so the probabilities on the second set of branches will be the same as the first. Can you work out the probability that he gets 2 heads, or 1 head and 1 tail? Oops, let's go back. I want you to pause the video, draw this out with a ruler, please. Don't just sketch it out with freehand, with a ruler, for flipping the coin once. So that's going to be for the first coin, that's for the second coin. Remember, it's not a half. He's given us the probability of heads. We can then work out tails. So pause the video, unpause when you're done. Okay, unpaused. Let's put in some labels first of all. So I've got, he could get heads or he could get tails. And again, for the second coin, he could get heads, he could get tails, we could get heads, we could get tails. Now for the heads, it says what the probability of heads is, 0.68. Now if you didn't know what to do with the decimal, you just write it along the branch here. So you might at that point want to pause if you didn't do it before and then redo it. Otherwise, let's carry on. Now what's the probability of tails? Now I know they add up to 1. So if I do 1, take away 0.68, I get the probability of what tails must be, which is 0.32. Now the heads, again, 0.68, tails, 0.32, heads, 0.68, tails, 0.32. It's independent. The flip of the coin for the first time does not affect it for the second flip. And that's worth keeping in mind. Even if you flipped it 50 times and every time you've got a head, now in real life you're probably thinking, well, surely the next one's a tails. But actually the probability, the theoretical probability, has not changed. This is definitely a biased coin though. Should be 50-50, shouldn't it? Okay, what's the probability he gets 2 heads? So we've done the probability tree, so you get a mark or 2 for that in your exam. But the probability of head and another head is 0.68 times by 0.68. 8. Let's do that in the calculator, which is 0.4624. 0.4624. So that's the answer to the first one. There's only one way of getting 2 heads, and that's it. What about the probability of 1 head and 1 tail? Let's change pen color. Well, that would be, for example, getting a heads first and then tails, or could be, of course, tails and then heads. So the heads and then tails would be 0.68 times by 0.32. And the tails and then heads would be 0.32 times by 0.68, which should have the same answer because multiplying you can do either way round. 2176. So 0.2176. I know that's got the same answer for both. So 1 tail and 1 head would be either head and then tail, or, so I'm going to add 1 tail and 1 head in either order. So because it's that one or that one, I add the 2 together, which is 0.4352. 4352. Okay, we're not sure. Maybe go back and listen again. I'm going to start speeding up a bit. Another one for us to have a look at. So Angelo is playing a game with 2 fair dice, and they're fair, okay? That means there's, in theory, an equal probability for every outcome. She rolls both dice and wins a point for each die. That's really the singular of dice, right? So each dice that lands on a multiple of 3. So what are the multiples of 3 on a dice? I think you could probably figure this one out. Which are the multiples of 3? Well, that would be 3 or 6. Complete the tree diagram in which M stands for a multiple of 3. Okay? And I'll give you a bit of a clue here. And you've got to calculate these probabilities. Remember, you get 1 point. Wins a point, 1 point for every multiple of 3 that she gets. So I would label it like this. M and then M dash. Remember, M dash means, oops, not M is what that means. All right? So M and M dash. Okay, pause the video, unpause when you've answered the question. Unpaused. So let's go M, M dash, M, M dash. Now the probability of getting a multiple of 3, well, there are 2 ways to get a multiple of 3 out of 6. Okay, now you could put 2 6. Why not? You might have put 1/3, but that's fine. Now if it's 2 6ths for M, it's going to be 4 6ths for M dash. So either 1/3 or 2/3 if you did it like that. But both are perfectly acceptable. But the probability doesn't change for the second time you roll the dice. 2 6ths and 4 6ths, and 2 6ths and 4 6ths. There we go. So what's the probability she gets 2 points? Well, the way of getting 2 points would be getting a multiple of 3 and then another multiple of 3. So 2 6 and 2 6. So we're going to times one and the other. So 4 over 36. Or you might have put 1/9. Okay, let's put that over there as well, or 1/9. Either of those is absolutely fine. Tick. What about 1 point? Okay, well there are 2 ways to get 1 point. Let's just persuade my Mac that actually it does have enough power. Turn on the power. She's got the power. Wasn't me, that was someone else. Okay, so 2 points and 1 point. Right, there are 2 ways of getting 1 point. You might get the point from the multiple of 3 and then not get one. Or you might get not get a point the first time, but get a point the second time. Okay, both of these outcomes will give us 1 point. So this will be 2 6ths times by 4 6ths, because that's the journey I need to take. 2 times 4 is 8. 6, 6, 36. And you, of course, might have done that simplified to get 2/9. Now, the journey to get to this point, not a point and then do get a point, would be 4/6 times by 2/6. Again, 8 over 36. Now, I want 1 point. So there's 2 ways of doing that. Either point and then no point, or no point and then point, both of which have the same probability. I want this one or this outcome. Add them together to get 16 out of 36, which you might have got as 4/9. Okay, any of those are absolutely fine. So 16 over 36 or 4/9. Anything equivalent to that is fine. And then lastly, 0 points. There's only one way of doing that. That's the probability of getting no points, nil point, and no points, nil point. So 4, 6, and 4, 6. We're going along the branches, so we multiply. I want that outcome and that outcome. 16 out of 36, which again would simplify to 4/9. Okay, either of those, absolutely fine. Cool. I'm sure you're really good at these, which is why we're only going to do one more before we move on. Right, a spinner has 4 equally sized sectors, 3 grey and 1 white. There it is. The spinner's going to be spun twice. There's the probability tree. Calculate the probability that we get either the same colour or grey on at least 1 spin. Think about what that means. Off you go. Pause the video. Unpaused. Okay, so what's the probability of getting grey? That's 3/4 or 0.75. And white is 1/4 or 0.25. And it's the same every time we spin it. So the probabilities on the second set of branches will be the same. I'm actually going to work out all these different outcomes this time. It might save some time later. Probability of this would be 3/4 times by 3/4, which equals 9/16. This one is 3/4 times by 1/4, which equals 3/16. This is 1/4 times by 3/4, which is 3/16. And 1/4 times by 1/4, which is 1/16. Interesting, if you added up all of these probabilities from all the different outcomes, they will also add to 1. All right, what's the probability that we get the same colour then? Well, there's 2 ways of doing that. Either green, green, or white, white. Did you spot that? So you've got 9/16 or 1/16. So either of those would be fine. We want this one or this one, so we add 10/16. Or I suppose you might have put 5/8. Change colour for the other answer. What about grey on at least 1 spin? Grey. Well, that could be this one with 1 grey, or this one with 1 grey, or this one. It said at least. So 2 greys is also a possible outcome. So I want either 9/16 or 3/16 or 3/16. All 3 of those outcomes, one or the other or the other, which is 15/16. There's only one option where I don't get at least 1 grey. Okay, so do spot those. Look for the wording in the question. I did say only one more, didn't I? Still, this is an actual exam question, so it's definitely worth having a look at. I'm not going to read it to you. I want you just to do it like you've met it in an exam. Off you go. Okay, now if you weren't sure what the question was, I don't think it's written there, but it should be complete the probability tree. So sometimes they don't even ask you to work out the probabilities, but I think what we'll do here, if you haven't already done so, I want you to work out what the 4 different probabilities are at the end. So if you haven't done that already, work it out, pause the video, and then unpause when you're done. But as it is, I'm going to work them out now. So win dash, so not win. What about this one where we don't win? and then we do win. So win dash and then win, and then lastly win dash, because we're not going to win either of those. Remember, the little dash means not. Okay, so what's the probability that she doesn't win at badminton? Well, it must be 1/10. What's the probability she doesn't win at tennis, though? Well, if it's 2/5 for winning tennis, it must be 3/5 for losing tennis. She's definitely better at badminton. But the probabilities on this second set of branches are still independent, even though they have different probabilities to the first set, because it's a different event. But they're still independent. Let's put in some answers here then. So win and then win. We're going along the top edge of this probability tree. So we have 9/10 and 2/5, and we are going to do one and the other, so that one and that one. So you multiply 18 over 50. Don't bother simplifying it, you don't need to. Win and then not win. So winning at badminton is still 9/10, but losing at tennis is 3/5. We want this one and this one, so we multiply. So that is 27 over 50. Not win and then win. So not win at badminton is only 1/10, but winning at tennis is 2/5. So multiply the tops, 2, multiply the bottoms, 52/50. And lastly, what about losing at both? So losing at badminton, 1/10, losing at tennis, 3/5. We want one and the other. We want to lose at both. So we multiply the tops, multiply the bottoms, 3/50. Okay, that was just a quick one, wasn't it? Let's move on to the sweet spot, which is dependent events. This is a few more marks usually for this. So, examples again of this where one outcome of the outcome of one event is going to affect the outcome of the other. So picking counters from a bag and not replacing them. Let's see. So, that's going to be dependent. Different biscuits from a tin and eating as you go. So you pick a biscuit. What's the chance? One of those multi-packs. What's the chance it's a bourbon? Well, you take it out. It is a bourbon. You eat it. Next time you take a biscuit, the probabilities have changed because there's one less biscuit. But you're a happier person. A card is chosen from a deck and not replaced. Again, you take a card out. Is this your card? Then you keep it out of the deck, and then you take another one. There's one fewer cards in the deck of cards. I should have said fewer biscuits as well, shouldn't I? It's not less, it's fewer. Every time you take one out, there's one fewer card, and so the probabilities change. If you select one item and don't replace it before selecting, these are dependent events. So, classic kind of question. A box contains 8 milk chocolates and 4 plain. Linda is going to choose a chocolate at random, eat it, and then choose a second. Calculate the probability that Linda gets either 2 milk chocolates or one of each, so milk and a plain. Okay, I want you to have a go at this, remembering that the outcome of one is going to be affected by the other. So what are you going to do for the probability? So I just want you to have a go. Keep in mind what we've done, but check those probabilities on the second set of branches. So pause now. You've unpaused. Now we might get, what have we got? Milk or plain. So milk or plain, milk or plain. So the labelling is going to look, depending on how you've written it, something like this. Either milk or, no, not B. What's B? That's just weird. Let's try that again. So milk or plain, milk or plain, milk or plain. Okay, we have 4 plain chocolates. Let's call that plain. And let's go back to the milk chocolates. We have 8 milk. So let's say we take a chocolate out. Well, the probability of milk is 8 out of, well, 12, because there's 12 chocolates in all, 8 and 4. And the probability of plain is going to be 4 out of 12. And that adds up to 1, 8/12 and 4/12. So let's say that we go along this top edge. We've selected a milk chocolate. And so we're now on this top set of branches. We took a milk chocolate out, ate it, yum, yum, yum. So there's one fewer milk chocolates now. Let's get down to that blue pen. So there are now 7. So what's the probability of milk the second time? Well, it's 7 out of, well, it's not 12 anymore, because actually there's also 1 fewer chocolate overall. It's actually 11. 7 out of 11. Let's change colour. But the plain chocolates, now if I've gone across this top set, it means I selected a milk, so there's still 4 plain chocolates left out of 11. So the total's the same. Remember, 7 elevenths, 4 elevenths, that adds up to 11 elevenths. Cool? Right, so let's just go back to the start and reset it. Let's say that actually the first time out, I selected a plain chocolate. I came across this bottom branch, I selected a plain chocolate, so now there's 1 fewer plain chocolates. So 4/12 plain. Now, what's the probability of plain now? Well, now there's only 3 of them out of 11 because there's 1 fewer, so there's only 11. But the milk chocolates in this case would be still 8, but out of 11. It's 1 fewer chocolates, but there's still 8 milk because I came down this way. Remember, each sort of branch is like a pathway to an eventuality, an outcome, and there are 4 different outcomes at the ends. Let's just change to a red pen now, and let's start answering the question. So what's the probability of a milk chocolate and then another milk chocolate? Well, that would be 8/12 times by 7 elevenths, because those are the 2 probabilities going across the top of my branches. So 8 7s are 56, and 11 times 12 is 132. 56 out of 132, and don't simplify it, just leave it like that. So that's the first one. So the answer for I is 56 out of 132. Tick. What's the probability of one of each, milk and plain, but not necessarily in that order? Well, there are 2 ways of doing that, of course. Could be milk and then plain. Done again. Or it could be plain and then milk. So I need the probability of both of these outcomes. Well, this one would be 8/12 times by 4 elevenths. And this one would be 4/12 times by 8 elevenths. That's 32 out of 132. And this one is also, as it happens, yep, 32, just double checking I've got my maths right. 32 out of 132. Now, obviously for this one, I want either of those outcomes. I want either the first one or the second. So I add my 2 probabilities together. 64 out of 132, or equivalent. Yeah, if you simplified it, that's fine, but you just don't need to. Cool. Okay, so hopefully you got that right. If you didn't, here's another chance. A bag contains 5 counters, 3 white and 2 black. 1 counter is selected and not replaced, then another is selected. Work out the probabilities that the counters will be either the same colour or different colours. Okay, they are not replaced. It's a dependent event. There we go. So you've got you've got everything you need. Pause the video, unpause when you're done. Okay, so let's do this. Let's unpause. Off we go. So 3 white and 2 black, and they're going to not be replaced. So we could have white or black, or white or black, or white or black. And the whites, the probability the first time you take one out, the probability of white is 3 out of 5. And the probability of black is 2 out of 5. Now let's say we've gone along these top branches and I selected a white. Well, there's 1 fewer white now. So now there's only 2 whites out of 4 because there's 1 fewer counter altogether. But there are still 2 black, so that's 2 out of 4. Okay, fair enough. Let's do the bottom set of branches. Now if I've gone along the bottom set of branches, That means I've come down this way, and so I've selected a black counter, so there's one fewer of those, which means there's only 1 out of 4 which are black counters now. But the whites are still 3, so that's 3 out of 4. So that's what your probability tree should look like. Let's just get rid of those marks up there. Right, next. So work out the probability that counters will be the same colour. So there's 2 possible outcomes for this. It could be white and then white, or indeed it could be black and then black. Either of those outcomes, so I want one or the other. But we're going along the branches first, so I want white and I want white. So 3/5 times 2/4, which is 6/20. Black, black. That will be 2/5 times by 1/4, which is 2/20. Now I want one or the other. So if I'm doing the answer to question A, it could be either white, white, which is 6/20, or it could be black, black, which is 2/20. And because it's or, I add them together, 8/20, or equivalent. What about different colours then? Well, that's going to be some different options here. That could be white and then black, or possibly black and then white. There's my 2 options. Well, this path to get here is 3/5 and 2/4, so I need to multiply those to get 6/20. Or black and then white, I get black first, 2/5. I then get white, which is 3/4. Multiply the tops, multiply the bottoms. And so if I'm doing B, those are my 2 options. I could have white and then black, which is 6/20. Or, so I'm going to add 6/20, which is black and then white, which is 12/20. Okay, cool. Couple more then. So these definitely need practice. 2 boxes contain black and white counters as shown, bag A and bag B. A counter will be picked from bag A and placed into bag B. A counter will then be picked from bag B. Work out the probability the counter will be white. So what's the probability that the counter for the second bag will be white? So let's go. Well, oh, you're going to pause, aren't you? Sorry, I'm going to keep quiet. Pause first. You do the question first, and then we'll unpause in a minute. Okay, I've unpaused. So, of course, I could, again, have black or white. Black or white. Black or white. Now, the first probability that I select on the first go for selecting a black, well, that's 2 out of 3. There are 2 black counters out of 3, and white would be 1 out of 3 because there's 1 out of 3. Okay, let's go across this top branch. Now, if I went this way, I selected a black counter out of the first bag, and I put it into the second. So the probability of getting a black now is going to be 3 out of 5. Now, the probability of white will be 2 out of 5. Okay, does that make sense? Hope so. Right, let's reset that. Let's get rid of that extra counter I put in. Let's put it back in bag A. And this time, let's say I went across this bottom branch. That means I selected a white counter, so that's no longer in bag A. It's now in bag B. So the probability of white now is 3 out of 5. But for black, it's 2 out of 5. Now, this is the question. What's the probability that the second counter is white? Now, there's 2 possible ways that's going to happen. Either I get black, and then I get the white counter, or possibly I pick out a white from the first one, but then a white from the second. This is the thing. It wants me to have that the counter will be white. I want the one from the second bag, so these are the 2 outcomes, either this one or this one. But first of all, let's work out each individual one. So 2/3 times by 2/5 is black and white. So that's 4/15. And then white would be 1/3, and then 3/5. And I'm going to multiply those as well, because I want white and then white. So 3/15. Now I want one or the other. So we're doing either black and then white, or, so I do an add, white and then white. So 3/15, 7/15. I like this question because it's slightly different to the others. It mixes things up a little bit. Oh, here's a classic old My Maths question. Remember, we've got Q and E. We have a person with some. Wait, you can read it, right? I'll read it to you in a minute. You pause. You do the whole thing. Fill out the tree. Answer those questions down there, and then we will unpause. Okay, unpaused. We have a purse with 48 American quarters, Q, and 30 euro coins. Without looking, you pull 2 out at random. This is without replacement, because I'm taking them both at the same time. Right, but obviously I can only look at one at a time. Now what's the probability on the first branch that I get a quarter? Well, that's 48 out of a total of 48 plus 30 is 78 coins. So 48 out of 78. And there are 30 euros, so 30 out of 78. Let's say I've gone across this top branch though. Now if I take a quarter out, there's one fewer quarter. So that's only 47 quarters. There's also one fewer coin, 77 coins. But the euros, well, I haven't taken a euro yet, so there's still 30 euros out of 77 coins. It's going to be the same denominator for here because there's one fewer coin. It was a quarter that I looked at first. Bottom branches then, so 30 out of 78. So if I went this way, I selected a euro. So now there's one fewer euro. There's 29 euros out of 77 coins because I took one coin out. And the probability, the second one I look at is a quarter. Well, there's still 48 quarters out of 77 coins. I didn't take a quarter, I took a euro, but there's one fewer coin. Or coins. Okay, probability of Q. Well, QQ is across the top here. That's 47. Sorry, let's start with the right way around. 48 over 78 times by 47 over 78. So 48. I'm just doing this in my calculator because this is the first time we've had a question where the fractions are a bit big to take a long time to do it by hand. Okay, now I don't know whether it's simplified this or not. I'm just going to give you what my calculator gave you because that's probably how you did it. 188 out of 507, or anything equivalent to that will also be fine. So 188 over 507. Probability of Q and then E. Now this is not one of each. This is specifically Q and then E, which is this path in here. So that's 48 over 78 times by 30 over 77. So 48 over 78 times by 30 over 77. And this one, 204 over 1001. Or equivalent. And then no match. So what's the probability of no match? Well, that is two options. That's going to be the quarter and then euro, or euro then quarter. That's what they mean by that. Now the euro then quarter will be 30 over 78 and then 48 over 77, which is probably the same answer, but let's check it. 30 over 78 times by 48 over 77, which is the same thing, yeah, 204 over 1001. And I want both of those options because it might have been either that way round, so quarter then euro, or, so I'm going to add euro and then quarter, so 204 over 1001. which is... Oh, did I just write my answer down wrong? Let's just double check that. Oh, I would be really annoyed with myself if I have done that. So 78 times by, I'm just double checking my answer here. Always good to check your answer. That's 240, not 204. I bet you was thinking, why is he doing that? That's wrong. 240. Let's just rub those. In fact, I could rub them all out, couldn't I? Let's do them all. Erase it. That's the whole point of a rubber, isn't it? Just erase everything. So 240, 240. So 480 over 101. And let's just correct these. 240. I just misread my calculator. So 480 over 1001 or equivalent is fine. Okay, it's all about reading those questions. Last one. This time I've got some 10p coins and some 5p coins. 3 coins are picked at random without replacements. So we're going to pick 1, pick 2, pick 3. With that replacement, complete a probability tree for the 3 events. Okay, I'm not expecting you to do the probabilities at the ends of the branches. I just want you to complete the probability tree. So off you go. Pause and then unpause when you are done. Now this is the last one of this, I promise. And if I've set you some questions afterwards, there won't be many because you've done so many in this lesson. So it could be a 10p or a 5p. Each time we have option for 10p or 5p, 10p or 5p, 10p, 5p, 10p, 5p, 10p, 5p, 10p, 5p. Okay, when you get to 3 options, oh, it's not 3 options, 3 events, it all starts getting quite large, doesn't it? Right, there are 8 10 pences. And there are 5, no, there are 6, read the question, 6, no, why have I put a fraction? What's going on? I'll tell you what, it's because I'm not using another colour. Let's use another colour for this. So there are 6 5p's. Oh, apologies to people working in another country here, because you will obviously think, what's 10p and what's 5p? What's that all about? Just think of it as cents or dollars or something. So a jar, right, 3 coins picked at random. Well, the first one, the probability of 10p is easy, isn't it? 8 out of 14, because 8 plus 6 is 14. And then this will be 6 out of 14. Right, now if I go across this top branch here, I have selected a 10p, which means there's 1 fewer of those. So my probabilities are now 7 out of 13 and 6 out of 13. But, in fact, let's keep going that way. Now, if I keep going across the top here, if I select another 10p, there's 1 fewer again. So there will be 6 out of now 12, because every time I'm taking a coin, there's 1 less. But it's still 6 out of 12 for the 5s. Right, let's reset it, but let's go. So we still took a 10p the first time, but then we took a 5p the second time. So let's reset that. So where are we going? Right, so I came across this top branch and I took a 10p. But then I came down here, and that means I took 5p. Okay, so now the probability of 10 is going to be 7 out of 12. And the probability of 5 will be 5 out of 12. Again, make sure every time that your pairs of branches add up to 1. And let's go back now right to the start. Let's go back and say we went a completely different way. Completely different set of things happened here. Which is, I came down this path, and so I selected a 5p coin. That means there's 1 fewer of those, so it's 5 out of 13. 8 and 5 is 13. But there's still 8 10p's, so that's 8 out of 13. And let's keep going across the bottom. If I did it again, I'll have selected another 5p. So there's now 4 out of 12 coins, but still 8 out of 12 for the 10s. And lastly, in here, we sort of need to back up a little bit. If we end up in that point, that means that I came down here and selected a 5p. But I've gone up this journey and selected a 10p. So now, 10s, there are 7 out of 12 10p's. And the 5p's, there are 5 out of 12. So there's my probabilities. And if I was going along the branches here and working out the probability of a 10, another 10, and then a 10, I didn't ask you to do this, but if I did, it would have been 8/14 times 7/13 times by 6/12. You know, if you've got 3 probabilities and you're going along the branches, multiply them all together. Okay, well done. Mammoth one, that one. But good, I think we covered just about everything to do with the probability trees, except for algebra. Do that next time. All right? Okay, well done. Bye-bye.